Hi, welcome back to my channel. Well, in this video we'll try to learn some of the basic concepts which are involved in row column design, and whenever we are in a position to allocate treatments in rows and columns, and in context of field experiments, if the fertility gradient is moving in two directions, this type of design is used. When the experimental material is divided into rows and columns and the treatments are allocated such that each treatment occurs only once in each row and each column, such type of designs are known as lead square designs. In context of the field experiments, if the direction of the fertility gradient is known and it is moving in two directions, under those situations or circumstances, this lead square design is highly recommended. Lead square designs are normally used in experiments where it is required to remove heterogeneity of experimental material into two directions. That is why it is known as two-way elimination of heterogeneity. While as randomized complete block design or RCBD, it is known as one-way elimination of heterogeneity. In lead square design, the number of rows are equal to the number of columns, and the number of treatments are always equal to the number of rows, which are equal to the number of columns. Now, in this design, eliminating fertility variation consists in an experimental layout which will control the variations in two perpendicular directions. If we will take an example of LSD 5x5, it means we have to evaluate 5 treatments which are adjusted in 5 rows and 5 columns. So the randomization is done in a way, if we take an example of this A, suppose we have 5 treatments A, B, C, D, E, that means we have got 5 columns and 5 rows, and we have to allocate these treatments in such a way so that each treatment occurs once in each row and each column. If we take an example of this A, it occurs only one in this row and it occurs only once in this column. Take an example of E, it occurs only once in this row and it occurs only once in this column. So this is the way how we randomly allocate the treatments in lead square design. Now, as far as the statistical analysis is concerned, the model of lead square design consists of Yijk, which is the observation on the ith treatment, jth row and kth column. Mu is the general mean or grand mean. Ti is the effect of ith treatment. Rj is the effect of jth row. Ck is the effect of kth column. And this error is always random in nature and follows a normal distribution with zero mean and constant variance. Now, what are the different steps? These are the traditional steps which you used to do to gather the ANOVA table of any design, but in this case we used to start with the correction factor. This is the normal way in generating the analysis of variance of any design. That means square of the grand total divided by the number of rows multiplied by number of columns. Treatment sum of square, the sum of each treatment total divided by the number of treatments minus correction factor. In case of row square, in case of column square, we have to get the totals of row, we have to get the totals of the column in case of columns, and divide the sum of squares with the respective number of treatments, because in all these three cases the number of treatments are equal to the number of rows which are equal to the number of columns. That is why T is constant in all these denominators, and every sum of square has to be deducted with the correction factor to get the corrected sum of square. Total sum of square is squaring each and every individual observation and deducting it with the correction factor. Then error sum of square is very easy to calculate, like we used to do in the conventional analysis of variance. So deduct all the sum of squares, we will get error sum square. Once we get the sum of square, we need to put them in this ANOVA table. But this is very important. The degrees of freedom for rows, columns or treatment are same because of the fact all these things are equal. And error degrees of freedom in this case is T minus 1 and T minus 2. Once we have got the sum of squares, we divide them with their respective degrees of freedom. I have to calculate three F calculated values. One belongs to rows, another one to columns, and the third one to treatments. And in order to get a tabulated value, we need to get the degrees of freedom due to the source of variation. For example, T minus 1 is constant in all these three cases, and error degrees of are constant here. So in this way we can get the F value calculated and as well as for tabulated. So in this design, what we used to do, we used to get the mean square due to rows, due to columns and due to treatments. Then we need to authenticate whether the rows are significant, columns are significant or treatment effects are significant. For that we need to calculate the F or F test or variance ratio test, which is the ratio of two variances. One is due to the rows, another one is due to the error. In case of columns, it is the ratio of mean square due to columns divided by mean square due to error, and in case of treatment, it's the mean square due to treatment upon mean square error. And the thumb rule is whenever this calculated value of F is greater than this tabulated value, then we have to reject the null hypothesis. Now, if we take an example, an experiment on tomato was conducted to study the effect of foliar application of urea in combination with the insecticidal sprays in a cotton yield. So we have a 5 by 5 latent square because we have got 5 treatments, 5 which are adjusted in 5 rows and 5 columns. The randomization, they have been randomly allocated into these 5 rows and 5 columns in this table. Now the null hypothesis here is that rows, columns and treatment effects are equal. So the first thing is use the basic arithmetic operations, get the row totals, get the treatment totals. So we start with the correction factor, that is the square of the grand total divided by the number of observations. Since it's a 5 by 5, that is 5 multiplied by 5 is 25. So 1535.07 is our correction factor. Then row sum of squares is simply, this is the square of the first total up to this the last one, then divided by 5 minus the correction factor. Similarly for column sum of squares, we have already got the column sum of square. For example, this square plus this plus this plus this plus this square, so 14.77 is the column square. Now treatment square, for that, for example, if we take the example of the first treatment, we need to identify this treatment first. 9.3 plus 4 plus 6.5 plus 9.5 plus 4.9 is 34. That is the square total of the first treatment. Like in the rest of the treatments, we can get the squares. So divide by 5 minus the correction factor. Then total sum of square is very simple. It is a squaring of each and every observation. Say 4.9 square up to 7.6 square. We have to square it every observation. At the same time, we have to add them. Then finally error sum square is very simple to calculate. So we have got all these sum of squares. Now we need to put them into the ANOVA table. So we have 1, 2, 3 and 4 sources of variation. One is due to rows, another one is due to columns, and third one is due to treatment, and we have the error. And in other design, we used to get this calculated F, then we need to tally it with our tabulated F. Since in the first, if we talk about only about the treatments, the calculated value of F is greater than its tabulated value, so we have every reason to believe that means all these treatments are significantly different from each other. That means we have to reject the null hypothesis in this case. Now in order to do the post hoc analysis, like in other design, we used to get this critical difference or least significant difference. Here the least significant difference is 2.11, and you can see T5 and T3, they are significantly different from each other because of the fact that means the difference between these two is greater than this standard value. Rest of the treatments are not significantly different from each other. So this is a design which is usually used whenever the treatments are arranged into rows and columns, and in context of the field experiments, whenever the fertility gradient is moving in two directions. So in those circumstances, we used to apply this design. So in next video we will start with the factorial experiments. Hope you will like this video. Thank you very much.